The Sun has a dark twin, and it's coming. What if the Sun isn't alone? What if, far beyond the edge of our solar system, hidden in the cold and the dark, something waits? For centuries, we believed the Sun was solitary, the center of our cosmic stage, the giver of life. But what if that belief is wrong? What if our Sun has a twin? Not a bright, blazing sibling, but a shadow, a dark star, a silent companion drifting through the void. Scientists have whispered about it for decades. They call it Nemesis, the hypothetical dark twin of the Sun. A star so faint, so distant, it hides from our eyes, yet its influence may shape the fate of life on Earth. Nemesis is more than a theory. It's a suspect, a cosmic culprit linked to patterns of mass extinction. Every 26 million years, life on Earth suffers catastrophic loss. Dinosaurs, ancient species, entire ecosystems wiped away. Could Nemesis be the trigger? Could its orbit disturb the icy graveyard of comets in the Oort cloud, sending death plunging toward our world? If Nemesis exists, it's not a star like ours. It could be a dim red dwarf, or a cold brown dwarf. Perhaps even something stranger, a black hole, cloaked in darkness, pulling the strings of cosmic chaos. And here's the chilling part. It might be coming closer. In this video, we'll explore the Nemesis hypothesis. We'll dive into the science, the speculation, and the unsettling possibility that our Sun has a hidden twin. We'll examine the evidence, the myths, and the psychological terror of an unseen destroyer lurking in the dark. Is Nemesis real? Is it watching? And if it returns, what will it bring? Welcome to the mystery. Welcome to the shadow. Welcome to Nemesis. The Nemesis hypothesis. The Nemesis hypothesis is one of the most intriguing and unsettling ideas in modern astronomy. It suggests that our Sun, the life-giving star at the center of our solar system, may have a hidden twin. Not a bright, blazing sibling like the stars we see in the night sky, but a dark, elusive companion lurking in the far reaches of space. The origins of this hypothesis trace back to the 1980s, when paleontologists noticed a disturbing pattern in Earth's history. Mass extinctions, catastrophic events that wiped out vast numbers of species, seem to occur at regular intervals, roughly every 26 million years. Dinosaurs, marine life, ancient forests, all victims of these periodic cataclysms. What could cause such rhythmic destruction? Some scientists propose that the culprit might not be earthbound, but cosmic. They theorize that something out there periodically disturbs the Oort cloud, the vast, spherical shell of icy bodies surrounding our solar system. When this cloud is perturbed, comets are sent hurtling toward the inner planets, triggering impacts that devastate life. Enter Nemesis, the hypothetical dark twin of the Sun. According to the theory, Nemesis follows a long, elliptical orbit around our star, taking tens of millions of years to complete a single revolution. As it swings through the outer reaches of the solar system, its gravity could jostle the Oort cloud, unleashing a deadly rain of comets. Nemesis was envisioned as a dim red dwarf or a cold brown dwarf, a star too faint to be easily detected. Some even speculated it could be a black hole, a silent predator cloaked in darkness. Whatever its nature, Nemesis would be distant, perhaps a light year away, yet powerful enough to influence the fate of life on Earth. The idea captured the public imagination. Headlines warned of a Death Star lurking in the void. Science fiction embraced the concept, weaving tales of cosmic doom. But for scientists, Nemesis was more than a story. It was a testable hypothesis, one that could explain the periodicity of mass extinctions. Researchers scoured the skies, searching for evidence. Infrared surveys probed the darkness, hunting for faint companions. Data from NASA's IRAS mission and later from WISE, Wide Field Infrared Survey Explorer, offered tantalizing possibilities, but no definitive detection. Nemesis remained elusive. Critics argued that the extinction pattern might be statistical noise, not a cosmic signal. Others pointed out that the dynamics of such a distant companion would be complex, and its orbit unstable over billions of years. Still, the hypothesis refused to die. It lingered in scientific discourse, fueled by the allure of mystery and the fear of the unknown. Why does Nemesis matter? Because if it exists, it reshapes our understanding of the solar system. It means our sun is not solitary, but part of a binary pair, a common arrangement in the galaxy. It means the architecture of our cosmic neighborhood is more complex and more dangerous than we imagined. It also forces us to confront a chilling truth. Life on Earth may be at the mercy of celestial rhythms beyond our control. The same forces that nurture existence could, in time, erase it. In the next chapter, we'll examine the evidence and the controversy. Why has Nemesis remained hidden? What have astronomers found, and what are they still searching for? The answers may determine whether Nemesis is a phantom or a predator waiting in the dark. Evidence and controversy. The Nemesis hypothesis sparked excitement and fear when it was first proposed, but decades of research have yet to confirm its existence. Why has this idea persisted despite repeated failures to detect a solar twin? The answer lies in the complexity of observation and the allure of cosmic mystery. When scientists first suggested Nemesis in the 1980s, they believed it could be a dim red dwarf or a cold brown dwarf orbiting far beyond Pluto. Such objects emit little visible light, making them nearly invisible to optical telescopes. Detecting Nemesis would require infrared observations, a challenge for technology at the time. Early searches focused on data from the infrared astronomical satellite, IRAS, launched in 1983. IRAS scanned the sky for heat signatures, cataloging hundreds of thousands of infrared sources. Some candidates appeared promising, but follow-up studies revealed they were distant galaxies or faint stars unrelated to our Sun. In the 2010s, NASA's Wide Field Infrared Survey Explorer, WISE, offered a more powerful tool. WISE mapped the entire sky in infrared, capable of detecting brown dwarfs within a few light-years. If Nemesis existed as a brown dwarf, WISE should have found it. Yet, the survey revealed no such companion. The absence of evidence led many astronomers to conclude that Nemesis, at least in its original form, does not exist. Critics argue that the extinction pattern Nemesis was meant to explain may not be real. Statistical analyses suggest the 26 million year cycle could be an artifact of incomplete data. Fossil records are patchy, and extinction events may cluster by chance rather than cosmic design. Still, the idea refuses to die. Why? Because the solar system is vast, and our knowledge is incomplete. A distant companion could lurk in regions we have barely explored. The Oort cloud, for example, spans trillions of kilometers. An object orbiting at tens of thousands of astronomical units would be extraordinarily hard to detect. Moreover, Nemesis has evolved in theory. Some researchers speculate it could be smaller than expected, perhaps a massive planet rather than a star. Others suggest it might be a black hole, invisible except for its gravitational influence. These possibilities keep the search alive. The controversy surrounding Nemesis highlights a deeper truth. Science thrives on mystery. Even when evidence is lacking, questions drive progress. The hunt for Nemesis has spurred advances in infrared astronomy, deep sky surveys, and our understanding of stellar dynamics. Yet, skepticism remains strong. Most astronomers now favor alternative explanations for extinction cycles, such as volcanic activity, asteroid impacts, and climate shifts. Nemesis, if real, plays no confirmed role. And yet, the cosmos is full of surprises. History reminds us that ideas once dismissed, like continental drift or dark energy, later reshaped science. Could Nemesis be another such idea, waiting for the right evidence? In the next chapter, we'll explore binary star systems. How common are stellar twins? Could our Sun be part of a hidden pair? The answers may reveal whether Nemesis is fantasy or fact. Binary star systems. Binary star systems are among the most common arrangements in the galaxy. In fact, most stars we observe are not solitary like our Sun. They exist in pairs or even larger groups, bound together by gravity. This raises an intriguing question. Could our Sun also belong to such a system, with a hidden twin lurking in the dark? Astronomers estimate that more than half of all stars in the Milky Way are part of binary or multiple star systems. These systems vary widely in their configurations. Some pairs orbit close together, exchanging material and influencing each other's evolution. Others are separated by vast distances, circling a common center of mass over millions of years. Binary stars form naturally during the birth of stellar systems. When a cloud of gas collapses under gravity, it often fragments into multiple cores, each forming a star. These stars remain gravitationally linked, creating a binary or even a cluster. Given this tendency, it would be unusual for the Sun to be truly alone. If the Sun has a companion, why haven't we seen it? The answer may lie in its nature. A bright twin would be obvious, but a dim partner, such as a red dwarf or brown dwarf, could hide in the darkness. These stars emit little visible light, making them nearly invisible to optical telescopes. Detecting them requires infrared observations, which have limits at extreme distances. The dynamics of binary systems depend on mass and separation. Close binaries interact strongly, sometimes merging or triggering stellar explosions. Wide binaries, separated by thousands of astronomical units, exert weaker influence but remain gravitationally bound. If Nemesis exists, it would belong to this latter category, a distant, slow-moving companion with an orbit spanning millions of years. Such an orbit would be highly elliptical, carrying Nemesis far beyond the Kuiper belt and into the realm of the Oort cloud. At its closest approach, it could disturb icy bodies, sending comets toward the inner solar system. At its farthest, it would vanish into interstellar darkness, undetectable by current instruments. Evidence for wide binaries comes from observations of other stars. Surveys reveal countless examples of stars paired with faint companions at enormous distances. Some systems include brown dwarfs orbiting far from their primaries, challenging earlier assumptions about stellar isolation. If the Sun is part of a binary, it would reshape our understanding of the solar system's formation. It might explain certain anomalies in planetary orbits, or patterns in cometary distribution. It could even account for periodic disturbances linked to mass extinctions. Yet, the search for a solar twin has yielded no definitive results. Infrared surveys like WISE have ruled out companions larger than Jupiter within a few light-years. But smaller objects, or exotic ones like black holes, remain possible. The vastness of space and the limits of technology leave room for mystery. The concept of Nemesis fits within this framework. It would be a wide binary companion, orbiting so far from the Sun that its presence is subtle yet significant. Its gravitational influence could shape the architecture of the outer solar system, even if we never see it directly. Binary systems also raise philosophical questions. If the Sun has a twin, what does that mean for our place in the cosmos? We imagine our star as unique, solitary, the center of our world. But in reality, it may be part of a larger dance, a cosmic partnership hidden in the shadows. In the next chapter, we'll explore the Oort cloud connection. How could Nemesis disturb this distant reservoir of comets? And what would that mean for life on Earth? The Oort cloud connection. The Oort cloud is one of the most mysterious regions of our solar system, a vast, spherical shell of icy bodies surrounding the Sun at unimaginable distances. It begins far beyond the orbit of Pluto and may extend halfway to the nearest stars. This frozen frontier is a cosmic graveyard, home to trillions of comets waiting in silence. But what if something, or someone, disturbs that silence? Enter Nemesis, the hypothetical dark twin of the Sun. If Nemesis exists, its orbit would carry it through the outer reaches of the solar system, passing near or through the Oort cloud. Its gravitational influence could jostle these icy bodies, sending them tumbling inward toward the inner planets. The result? A deadly rain of comets, some on collision courses with Earth. This mechanism offers a chilling explanation for periodic mass extinctions. Geological records suggest that catastrophic impacts have occurred throughout Earth's history, wiping out species and reshaping ecosystems. The extinction of the dinosaurs 66 million years ago is the most famous example, triggered by an asteroid or comet strike. But other events, spaced tens of millions of years apart, hint at a pattern. Could Nemesis be the trigger behind these cycles? The theory fits the timeline. If Nemesis completes an orbit every 26 million years, its close approach to the Oort cloud could unleash waves of comets at regular intervals. These icy missiles, drawn by gravity toward the Sun, would occasionally intersect Earth's path, with devastating consequences. The Oort cloud itself is a fascinating structure. It is thought to contain remnants from the birth of the solar system, primordial material preserved in deep freeze. Its vastness defies comprehension. Trillions of objects scattered across a sphere, perhaps 100,000 astronomical units in diameter. Detecting individual bodies is nearly impossible, making the cloud a hidden reservoir of potential doom. When Nemesis disturbs this reservoir, chaos follows. Comets dislodged from stable orbits begin long, perilous journeys inward. Some swing past the giant planets, their paths altered by gravitational encounters. Others plunge directly toward the Sun, their icy surfaces vaporizing into brilliant tails. And a few, just a few, strike Earth with the force of nuclear arsenals, igniting firestorms, tsunamis, and climate collapse. Evidence for such impacts is etched in stone. The Chicxulub crater in Mexico marks the site of the dinosaur-killing impact. Other craters, scattered across continents, testify to repeated cosmic bombardments. Fossil records reveal abrupt die-offs, coinciding with layers of iridium, a metal rare on Earth but common in asteroids and comets. The Nemesis hypothesis ties these clues together. It offers a cosmic clockwork behind Earth's cycles of destruction. But proving it is another matter. The Oort cloud is too distant, Nemesis too elusive. Infrared surveys have ruled out large companions nearby, but a smaller object, or one cloaked in darkness, could still lurk beyond our reach. If Nemesis exists, its influence extends beyond extinction. It shapes the architecture of the solar system, sculpting cometary paths and perhaps even influencing planetary orbits. Its presence would redefine our understanding of celestial mechanics and our place in a dynamic, perilous cosmos. In the next chapter, we'll explore even darker possibilities. Could Nemesis be more than a faint star? Could it be a black hole, a silent predator drifting through the void? The answers may be stranger and more terrifying than we imagine. Dark stars and exotic objects. When scientists first imagined Nemesis, they pictured a faint star, perhaps a red dwarf or a brown dwarf, orbiting far beyond Pluto. But as searchers failed to find such an object, speculation turned darker. Could Nemesis be something far more exotic? Could it be a black hole, a silent predator drifting through the void? Brown dwarfs are often called failed stars. They form like stars from collapsing clouds of gas, but never ignite sustained hydrogen fusion. Too small to shine brightly, they glow faintly in infrared, making them hard to detect. If Nemesis were a brown dwarf, it could easily hide in the darkness, invisible to optical telescopes. Infrared surveys like WISE have searched for such objects, ruling out large brown dwarfs within a few light-years. But smaller ones remain possible. A brown dwarf companion would exert gravitational influence without betraying its presence through light. It could lurk in the outer solar system, shaping cometary orbits while remaining unseen. Then there's the black hole scenario, the most chilling possibility. A black hole is the corpse of a massive star, collapsed into a point of infinite density. Its gravity is so intense that nothing, not even light, escapes. If Nemesis were a black hole, it would be utterly invisible, detectable only through its gravitational effects. A black hole companion would be small, perhaps the size of a city, yet immensely massive. It could orbit the Sun at a distance of a light-year, tugging subtly on the solar system. Its presence might explain anomalies in comet distributions or planetary motions. But finding it would be extraordinarily difficult. Detection strategies rely on indirect clues. A black hole might reveal itself through gravitational lensing, bending the light of background stars. It might betray its existence by accreting matter and emitting X-rays, but only if it encounters material to consume. In the emptiness of interstellar space, it could remain silent for eons. The physics of such companions is mind-bending. A brown dwarf would be cold, dim, and lonely, a ghost star wandering the dark. A black hole would be even more alien, a tear in space-time, warping reality itself. Both possibilities challenge our sense of security. They remind us that the universe is not just vast, but full of hidden dangers. Could Nemesis be something stranger still? Some theorists speculate about primordial black holes, relics from the Big Bang, scattered through the cosmos. Others imagine exotic objects predicted by speculative physics, boson stars, dark matter clumps, or even artificial constructs. These ideas stretch the limits of science, but they underscore a truth: the unknown is vast. Why does Nemesis matter? Because its existence would reshape our understanding of the solar system. It would prove that our Sun is not solitary, but part of a binary pair, a common arrangement in the galaxy. It would reveal that the architecture of our cosmic neighborhood is more complex and more perilous than we imagined. And it would force us to confront a chilling possibility, that life on Earth is at the mercy of forces beyond our control. A silent companion, orbiting in darkness, could dictate the rhythm of extinction. In the next chapter, we'll explore the human side of this mystery. Why does the idea of a hidden twin terrify us? What does it reveal about our psychology, our fears, and our fragile sense of security in a vast and indifferent cosmos? Human psychology and cosmic fear. The idea of a hidden twin star lurking in the darkness is more than an astronomical curiosity, it is a psychological trigger. Nemesis, if real, is not just a scientific concept, it is a symbol of our deepest fears. It represents the unknown, the uncontrollable, and the unseen forces that shape our fate. Humans are wired to fear what they cannot see. From the earliest days of evolution, survival depended on detecting threats before they struck. Predators hiding in the shadows, dangers lurking beyond the firelight, these primal fears are etched into our minds. Nemesis taps into that ancient anxiety. It is the ultimate unseen predator, drifting silently through space, capable of ending life on Earth without warning. This fear is amplified by scale. We live in a vast universe, yet our sense of security depends on the illusion of stability. The sun rises each day, the seasons follow their rhythm, and the stars seem fixed in the sky. Nemesis shatters that illusion. It reminds us that cosmic forces operate on timescales and magnitudes beyond comprehension. It tells us that extinction is not a question of if, but when. Existential dread emerges when we confront the fragility of life. Nemesis embodies that fragility. It suggests that our species, our civilizations, our histories, all could vanish in an instant, erased by a force we cannot control. This realization breeds a unique terror, the fear of meaninglessness. If everything can end without reason, what does it mean to exist? Psychologists call this the abyss, the confrontation with ultimate uncertainty. Some respond with denial, dismissing Nemesis as fantasy. Others embrace fascination, drawn to the drama of cosmic doom. Horror films and apocalyptic fiction exploit this tension, turning scientific speculation into cultural myth. Nemesis also evokes a fear of betrayal. We trust the sun. It is our source of life, warmth, and light. To imagine it harboring a dark twin, a destroyer hidden in its gravitational embrace, feels like a cosmic betrayal. It twists the familiar into the sinister, transforming comfort into threat. Yet, fear is not the only response. For some, Nemesis inspires awe. It expands our sense of scale, forcing us to see beyond the narrow confines of daily life. It reminds us that we are part of a dynamic, unpredictable cosmos, a universe that is not static, but alive with motion and mystery. This duality, terror and wonder, defines the human relationship with the unknown. We fear Nemesis because it threatens our survival, but we are fascinated because it challenges our imagination. It is both a nightmare and a narrative, a scientific hypothesis and a psychological archetype. In the next chapter, we'll explore how ancient myths echo these themes. Stories of twin suns, cosmic destroyers, and apocalyptic cycles may hold clues to humanity's enduring obsession with hidden forces in the sky. Ancient myths and modern parallels. Long before telescopes and space probes, humanity looked to the sky and imagined stories to explain its mysteries. Among these stories were myths of twin suns, cosmic destroyers, and cycles of creation and annihilation, narratives that echo eerily with the modern concept of Nemesis. In ancient Egypt, the sun was revered as Ra, the god who sailed across the sky each day and through the underworld each night. But some texts hint at a shadow companion, a force of chaos that threatened Ra's journey. This duality of light and darkness mirrors the idea of a bright sun paired with a hidden twin. The Greeks spoke of Nemesis as a goddess of retribution, punishing hubris and restoring balance. Though not a celestial body, her name resonates with the hypothesis of a cosmic nemesis, a force that brings destruction at regular intervals, enforcing nature's harsh equilibrium. In Hindu cosmology, cycles of creation and destruction dominate the universe's rhythm. The dance of Shiva symbolizes both birth and annihilation, echoing the periodic catastrophes Nemesis might trigger. These myths suggest an intuitive grasp of cosmic cycles long before science quantified them. Mesoamerican cultures envisioned twin forces governing the cosmos. The Aztecs believed in suns that rose and fell across epochs, each ending in cataclysm. Their myths of recurring worlds align with the notion of extinction cycles tied to celestial mechanics. Even Norse mythology speaks of Ragnarok, a doom driven by cosmic upheaval. Wolves devour the sun and moon, plunging the world into darkness before rebirth. This imagery parallels the fear of a hidden star disrupting the solar system, heralding chaos before renewal. Why do these parallels exist? Perhaps because humans have always sensed the fragility of existence. Observing eclipses, comets, and planetary motions, ancient cultures wove narratives to explain the unpredictable. Today, science replaces gods with gravity, but the underlying theme remains: unseen forces shape destiny. Modern parallels abound in literature and film. Stories of rogue planets, killer asteroids, and binary stars populate science fiction, reflecting our enduring fascination with cosmic threats. Nemesis, whether mythic or scientific, taps into a universal archetype, the destroyer hidden in the dark. These myths and modern theories share a psychological core, the tension between order and chaos. The sun represents stability, life, and light. Its dark twin symbolizes disruption, death, and shadow. Together, they form a cosmic yin-yang, a duality that defines existence. In the next chapter, we'll turn from myth to future speculation. Could humanity one day confirm Nemesis? And if so, what would that mean for our survival and our understanding of the universe? Future searches and speculation. The Nemesis hypothesis may be controversial, but the search for a hidden solar companion is far from over. Advances in technology and upcoming missions promise to probe the darkness like never before. Could Nemesis still be out there, waiting to be discovered? And if so, what would that mean for humanity? Future searches will rely on next-generation telescopes and all-sky surveys. Instruments like the Vera C. Rubin Observatory, with its powerful wide-field capabilities, will scan the heavens for faint objects at unprecedented depth. Its Legacy Survey of Space and Time, LSST, will map billions of stars and track their motions, potentially revealing subtle gravitational anomalies that hint at unseen companions. Infrared astronomy will play a critical role. Brown dwarfs and other dim objects emit most of their energy in infrared wavelengths. The James Webb Space Telescope, JWST, already revolutionizing our view of the cosmos, could help identify faint sources in the outer solar system. Future infrared missions may push even deeper, searching for heat signatures in the cold void. Radio astronomy offers another avenue. Exotic objects like black holes might interact with surrounding material, producing faint emissions detectable by sensitive radio arrays. Projects like the Square Kilometre Array, SKA, could uncover clues invisible to optical instruments. Gravitational studies will complement these efforts. Precise measurements of planetary orbits, asteroid trajectories, and comet paths can reveal perturbations caused by distant masses. If Nemesis exists, its gravitational fingerprint may already be imprinted on the architecture of the solar system, waiting to be decoded. Speculation extends beyond detection. If Nemesis is real, what are the implications? Its orbit could intersect regions of the Oort cloud, triggering comet showers that threaten Earth. Understanding its path would be vital for planetary defense. Missions to monitor and deflect hazardous objects might become a cornerstone of survival. Could we ever visit Nemesis? The distances involved are staggering, tens of thousands of astronomical units. Reaching such a target would require propulsion technologies far beyond our current capabilities, nuclear fusion drives, antimatter engines, or concepts like the Breakthrough Starshot initiative scaled to interstellar distances. For now, Nemesis remains beyond reach, a phantom glimpsed only through theory. If Nemesis exists, it challenges our perception of the Sun as a solitary beacon. It places our solar system within the broader context of binary star dynamics, aligning us with the majority of stellar systems in the galaxy. It reminds us that isolation is an illusion, and that hidden relationships shape the cosmos. And if Nemesis returns, the consequences could be catastrophic. A close approach might destabilize cometary reservoirs, sending icy missiles toward the inner planets. It could alter orbital resonances, triggering long-term shifts in planetary climates. In the most extreme scenarios, it could even eject worlds from the solar system, rewriting the architecture of our celestial home. Yet, Nemesis also offers opportunity. Its discovery would revolutionize astrophysics, providing a natural laboratory for studying stellar evolution, gravitational dynamics, and the interplay between stars and planetary systems. It would deepen our understanding of extinction cycles, linking Earth's biological history to cosmic rhythms. Ultimately, the search for Nemesis is more than a quest for a star. It is a confrontation with uncertainty, a reminder that the universe is vast, dynamic, and indifferent to human concerns. Whether Nemesis exists or not, the pursuit expands our horizons, forcing us to look beyond the familiar and embrace the unknown. In the end, one question lingers: if we find Nemesis, what will we do? Will we fear it, fight it, or accept it as part of the cosmic order? Perhaps the answer lies not in Nemesis itself, but in us, in our capacity to adapt, to imagine, and to endure.